here, and thanks to the organizers for letting me speak today. Yeah, maybe this talk is a little, on the conservative side of few body. It's really involving kind of two bodies that are colliding, but it's still few bodies, so it's in the kind of spirit. So hopefully we can play along. Be nice. So yeah, today I'll be telling you about charge-dipole resonant energy transfer. And resonant energy transfer is kind of a common thing. I think many people here are familiar with it. It has a lot of applications, one to biology and kind of biological processes like photosynthesis. You can even use it to do measurements, kind of positional or spatial localized measurements based on resonant energy transfer because of the high kind of sensitivity to spatial resolution. And so people use this in chemistry all the time in a technique known as fluorescence resonant energy transfer. And also there's applications to things like quantum information science where you can use things to transfer excitations from one particle to another, one atom, one molecule, and so on and so forth. So as here are some works, some examples. People now use optical tweezers to trap individual atoms or molecules, and you can build kind of baby quantum computers out of these things at the moment. So, very exciting stuff. And just to give a very broad overview of the mechanism I'll be talking about today. So really it's about a transfer of an excitation from one particle to another. So we're really looking at the excitation of a donor. So this is denoted D over here. So the donor is first energetically excited to an excited state. And then because of its resonant interaction, so these two particles, and here we're talking about just simple two-level particles, these two particles are now resonantly interacting. So the energy splitting is the same between these two particles, and they interact. And so the donor then resonantly interacts with the acceptor, and the acceptor can then take on the excitation, which is then transferred over. And so one famous example of resonant energy transfer is the Foster resonant energy transfer. And so you have these dipole-dipole interactions where two particles have a dipole-allowed, so a transition dipole moment between the two particles. They interact via this dipole-dipole interaction, and then this causes the transfer of an excitation over to the other acceptor. But this is really not what we're going to be talking about today, because I'm not going to be looking at dipole-dipole resonant energy transfer, but it's really, as the title alluded to, it's a dipole with a dipole-disallowed transition between the other, in this case, a Rydberg atom, which I'll talk about in a little bit. But so let me get some context and where this is coming from to begin with, and it comes from an experimental observation. So we're collaborating with the group at UCL, Stephen Hogan's group at UCL. And there they have a nice kind of experimental setup, and this is a molecular beam setup. And so they have kind of just a filament here, which has helium atoms spitting out of it. And they pass these helium atoms through this filter, which are then excited to their Rydberg state. So these are highly excited Rydberg states. So I think it's kind of, within the interval of 64 to 65, n equals to 64, n equals to 65 excitations of the Rydberg atom. And then, moreover, these Rydberg atoms are already interesting, but then they pump in a gas of ammonia molecules in their low vibrational ground states. And so these are, although these are kind of hot in the context of ultra-cold settings, which I'm maybe more familiar with, but these are hot in the kind of millikelvin regime. So these are still relatively cold. These molecules that they pump in, they can still address individually their individual low vibrational states. So these are energetically separated from the kind of temperatures they were dealing with. So to give a sense, the rotational splittings are around 10 gigahertz and the temperature is around 1 gigahertz. So these are kind of nicely energetically separated. To be honest, I'm a theorist, so I really don't kind of know more than anything about this setup. Just, maybe some of you who are experimentalists here, you look at this and be like, oh, okay, I get it now. Somebody gives me this diagram, I go, okay, I believe you. This is how science is done. The plot that I do recognize and I do understand is this. So there's some axes and there's some values. I kind of like these labels. And so what they actually do measure is an electronic signal. So they measure this kind of ionization signal of these Rydberg atoms at the end of the experiment. So they have some time over which the beam flows. And in the relative frame of the beam is where this 100 millikelvin gas is is kind of defined, this temperature is defined. And so in this propagating frame, the ammonia molecules are then colliding with the helium atoms. And so in this plot, what this plot is showing is that as a function of detection time, there's an electronic signal of the Rydberg atoms as they're ionized by an electric field. And so if okay, maybe this is a little hard to see, but there's a very faint blue solid curve that's kind of thin in its line shape. But you can see that if it's just pure helium through this beam experiment, only specific Rydberg levels are excited. And so there's only peaks in kind of the expected Rydberg excitation levels due to the laser excitation of these Rydberg atoms. But then now if you introduce these helium atoms, there's some other bumps that pop up here and there. And in particular, the one that we're kind of looking at is this third from the top line over here. I guess it's kind of in the middle. So it's the middle line over here. Oh, go back. Oh no. Which I've circled nicely. And really it's a transition that you see going from just the 65 state here, n equals to 65 state, you actually start to populate the 66, n equals to 66 state in the Rydberg atom as well, just by the introduction of ammonia molecules into these things. So this is kind of the process that we want to understand. And here's a measured percentage of the transition after the time that the beam occurs before the ionization time. So it's about 16% that they see of this. So it's kind of a small percentage, but statistically significant. And this is kind of what we want to understand. So the process we have in mind that explains this phenomena, or this observation, is a collisional resonant energy transfer. So these are things where the ammonia molecule then collides with the helium atom, and then causes this transition in the Rydberg atom to occur. So as I mentioned earlier, the ammonia molecules are in their specific rho vibrational state. So in this case, they're in the 1-1, so n equals to 1, mn equals to 1 rotational state. And in the vibrational ground state and the rotational 1-1 state. And the other thing about ammonia molecules is that they have an inversion symmetry. So they're parity doublets. And therefore you can think about it as, okay, there's this umbrella transition where you can flip the ammonia molecule from this configuration to this configuration. I don't know if I'm doing justice to this. But basically this flips to the bottom. And those are symmetric, right? I mean, those basically identical. But in quantum mechanics, of course, these states are not independent. And so they're talking to each other. So this causes kind of the interaction, this double well type potential, which causes the splitting of these two states. And that's the inversion, the famous kind of Masing transition in ammonia, of course, which is about 24 megahertz. So now we're bringing in the helium atom. So the helium atom comes in 65, n equals to 65. But as you might have noticed, the transition from 65 to 66, they're both in the L equals to 0 state. So they're both in the S state. So this is a dipole-disallowed transition, even though the inversion splitting of ammonia has a dipole moment in the molecular frame, right? So despite these two, sorry, I said megahertz, I think I meant gigahertz. But so despite these two energy levels being closely degenerate, so they're very, very close in energy, in principle, okay, if you have this kind of idea of a dipole-dipole resonant energy transfer, this cannot happen because this is a dipole-disallowed transition. But yet the experiment still sees it, right? I mean, so they see these reactants come in, and the products that come out, I mean, okay, this is really not a chemical reaction, but basically the ammonia molecule flips its inversion parity doublet, whereas the Rydberg atom gets excited to a 66S state. So what's happening over here? And we suspect that it's a charge-dipole resonant energy transfer phenomena or process that's happening instead of a dipole-dipole Foster resonance energy transfer. And let me walk you through kind of at least my understanding of the model and kind of the mechanism behind this. So this is the charge-dipole interaction. I think this is probably the only equation I'm going to show on the slides, but this is just to give some context. So there's a dipole moment in the ammonia molecule, again, from this inversion parity doublet that's splitting. And it's interacting with the electric field that's generated by the Rydberg atom. So this is the individual electron of the helium atom and the helium ion core. that are both generating electric fields and interacting with the ammonia molecule. So this is the charge-dipole interaction. And it becomes really significant when the ammonia molecule enters the Rydberg orbit. So when the ammonia molecule actually goes into this orbit, and then this interaction becomes very, very significant. Otherwise, you kind of think about it in this far field limit, they're kind of both these dipoles and they're playing around. And so really you want to think about dipole-dipole interactions. But over here, once you pass into this orbit, then you really get into this charge-dipole regime, which is what we care about. And this is allowed in these gases at the temperatures and the densities that we care about. So one thing I do want to point out as well is these helium atoms, these are really dilute gases that flow through. And so the Rydberg atoms, even though they're excited to the highly excited Rydberg states, these are basically non-interacting. They really don't talk to each other. And the relative density of the ammonia to the helium atom, that's what's most significant in the interaction regime, just to say that. So it's not Rydberg interactions that's causing this excitation. All right, so now the thing is, how does this happen? So you have this interaction, and how is this interaction really causing this excitation of the Rydberg atom from a 65s to a 66s state? It's because, okay, you have this term which doesn't really do anything. I mean, it kind of has the selection rules that the N's don't change and the L's don't change, so nothing really happens. You just shift the energy levels. But this other term over here, which is significant again in the Rydberg orbit, this has this multipole type expansion that's happening over here. And there's this YL0 term over here. And so if L prime equals to 0, this is a allowed transition that's happening. So you can actually bring L equals to 0 to L equals to 0 states in the Rydberg atom by the presence of this ammonia molecule because of this charge-dipole interaction. So this is kind of the basis for why this transition is allowed. And it's further enhanced by the fact that these two energy splittings are resonant with each other. And that's really what's causing this mechanism to occur. All right, so as I said, okay, so this term couples the interaction. And again, because there's an R dependence here with some kind of L power, this allows an overlap integral with the Rydberg states to give it a kind of effective dipole moment, even in the S to S transition. All right, so as you can see, here's an energy level diagram of the adiabats. So I want to look at the adiabatic potential energy surfaces of the 65s minus states. So this is one of the parity invergent states, the antisymmetric one. And then the symmetric parity doublet state of the ammonia molecule with 66s. So these are the two kind of adiabatic curves. And as you're coming in, and I think, sorry, and this is meant to be big R, not small r. But so as the ammonia molecule is coming in to the helium ionic core, the interaction causes this energy level repulsion in the adiabatic curves, which also means that these two curves are interacting. And so here's the actual transition matrix element that we compute as a function of the big R, which this was supposed to be. And you can see that only kind of behind this 400 nanometer range does this interaction become significant, and they can start having excitation between the diabatic energy levels due to this collisional type process that's happening. And one thing to note is that, okay, these are kind of mostly closely in resonance, but they still have some detuning between these asymptotic energy eigenstates of the non-interacting system. But this energy level is kind of small, and it's around 40 megahertz compared to the collision energy, which is on the order of gigahertz. So the collision energy can really kind of smear out this detuning that you have in the system. So, and then another thing to note is really there's no kind of electric fields or magnetic fields that are helping any other kind of dipole type processes in the system that are at least significant to see things, transitions that are happening here. All right. Yep, so as I mentioned, kind of this transition percentage that the experiment sees in about 16%. And we have a theoretical model to try and explain this. And so the components of the theoretical model, of course, involve this charge-dipole allowed transition. And again, this collisional energy helps to mediate this process by just energetically allowing this process to occur. So both channels are open in this process, in this collisional process. And so you can come in on the lower energetic asymptotic threshold and you come out on the higher one. And that's completely energetically fine. And then we also have a small kind of resonance detuning. This is kind of on the megahertz scale compared to the gigahertz scale energies that we're talking about here. And also there's this absence of accidental resonance. So other energy levels are pretty far detuned in energy, so we don't care about them. And so the theory, which is just a first order charge dipole theory, really predicts around 17%, which is pretty close to what we see in the experiment. So this is kind of encouraging to say that this is really the process that's happening and causing this transition. And we can also see, just to make the point extra clear, that there are no accidental resonance. We look at a few other states that are closely nearby, but not too much, not as much as the 66S, and we see a much suppressed signal over the 66S transition, which is kind of much lower than the noise signal that they can measure statistically.
So sorry, what do you mean by percentage? Isn't there a cross section? I'm not sure I understand what percentage means.
Yeah, so they just have a population measurement essentially. So they have some ionization signal at the end, and they take the ratios of this ionization signal. So the way that we compute this is we have some collisional rate, which we then integrate over the ionization time.
And this includes all partial waves, or are you treating the nuclear motion classically? What?
Yeah, so yeah, this is just a Born approximation that we do because the energy is just high enough, and we just use first order Born approximation. That's what I mean by first order charge.
What is the energy? Maybe you mentioned it.
Yeah, it's gigahertz. So the collision energy is about millikelvin.
And you say that's high enough to do the Born approximation?
So as I think, okay, maybe in terms of the language of partial waves, I think what we saw was energetically this involves about 25-ish partial waves. In principle, we could do a full scattering calculation, but the Born approximation seems to capture most of it, and this energy detuning here, it's really much smaller than the collisional energy, and so that's why we suspect it can just be encapsulated by the Born approximation.
Thanks.
Yeah. And also we have some, we drew some inspiration from references that say that it basically gets these kind of threshold laws correct. Certain energies, which is convincing enough at the moment for us. Cool, yeah. Are there any more questions, Ben? All right. So yeah, this was kind of nice and kind of encouraging for the theory. And then we can extend this kind of arguments or thoughts, or this train of thoughts a little bit more to just theory prediction. So as I mentioned earlier, we have this charge dipole interaction between the molecule and the helium atom. And in principle, we can think about applying magnetic fields to kind of tune the energy level spacing over here. So we can make this energy level spacing as a function of magnetic field. So this is true for helium, but of course for atoms with much stronger spin orbit couplings and things like this, you can really kind of tune the energy levels around. And in principle, you can tune it to resonance. So the experiment doesn't do this, but in theory, we can of course do this. So if we just use our first order charge dipole theory and we extend the analysis, we can see that in the experimental regime, the kind of transition probability is low. It was about maybe 16, 17%. But as we decrease the detuning, so we decrease the detuning between these levels, we can see that at some point you get very, very close to unit efficiency. And here, it's a weird scale, but this is in percentages. So 10 to the 2 means 100%. It's perfectly efficient transfer of this interaction. And so, yeah, here, in this regime, then you really get this kind of perfectly resonant energy transfer, which is very favorable if you want to do just kind of, things like measurements and maybe excitation transfer and kind of describing maybe some biological processes that Foster resonance theories maybe might not describe. So here's a possible application. So people now are very excited about these kind of hybrid molecule Rydberg platforms. And yeah, so in principle, you can use this kind of charge dipole interaction theory. If you can bring your optical features close enough, which people can move around now, kind of it's done all the time. If you bring them close enough and you bring really the molecule into the orbit of the Rydberg atom, you can induce this kind of resonant energy transfer between S to S, so dipole-disallowed transition, which could be exciting for Rydberg atom excitations. And So this work was done in collaboration with people here, Hussein and Steve. This is Stephen from UCL and Rosario. Actually, how much time do I have? Quite a bit of time. What time does my thing end? 4:15?
Yeah. I think
Oh,
we
okay, so-
started At 3:50, so you have some time.
Okay.
You still have
Then okay, cool. Then I'll switch gears a little bit to talk about a little something else. This wasn't in my title, but I thought it was kind of cute project on the side as well. Wait, but by some time you mean like 2 minutes?
the speaker should have 30 minutes, right? Yeah, so you have 5 minutes.
Okay. Okay, then maybe I'll stop here and just
Okay.
do for questions. Yeah, sorry. All right. Yeah, thank you. Yes.
So could it not just be a quadrupole transition?
Sorry.
Can
No,
it
it's
be-
also quadrupole forbidden.
Yeah, but the radiative quadrupole. I mean, if you come close by, then you have gradients in the electric field of the light field, and then you can have a quadrupole.
S to S is quadrupole
Yeah,
forbidden.
So it should also be quadruple disallowed. By what do you mean by radiative? Sorry.
By having like the next term, like if you expand the plane wave, yeah, then you get the IKR term, which gives you R squared in the dipole matrix, or the quadrupole matrix element, and then you can have a S to S.
But it's quadrupole forbidden.
You mean you okay. But you're invoking this kind of, you're saying the quadruple from the collisional portion?
No, from the photon, from the light field.
The,
You take some angular momentum from spatial angular momentum. Like if you have the e to the AKR of the plane wave and you expand it, then you get 1 plus AKR R, and then you have an R squared term
which light field are you referring to?
of the molecule, and you have this dipole transition. Is that no?
Oh, you're saying. Maybe I'm
He says no. So
Right?
This is forbidden. S to S is quadrupole forbidden. Yes, it's clear.
Yeah, I'm not sure if I'm confused by the line.
okay, so
We can talk.
I discussed with you.
Yes.
Could you go back to where you showed the multiple expansion?
Yeah.
Here's my one thing.
Yeah, I did drop some terms, that's why you're.
Yeah, I thought you said this, the real action is when the molecule is inside the Rydberg cloud. So, I mean, this capital R over little r, doesn't that need to have like the R greater, R lesser?
Yeah, I've dropped the R greater term, so I'm assuming that it's already inside this group.
That doesn't lead to any divergences in the integrals?
You mean because of the one of our small r over there? Yeah, so in practice, we truncate at the short range at some short distance, which in this case, we're kind of approximating by the thermal de wavelength. Because we're assuming these trajectories are kind of classical and the spread of these wave functions small. So there's some, there's some approximations.
Does that work harder to do the integral correctly, you're saying?
Yeah,
You
basically.
think it's justified? Okay.
Yeah.
That's a very nice point.
Yeah, I mean, it's basically what it is. Yes.
I'm curious, this ammonia inversion doubling, it's a really special property of this molecule.
Yeah.
Are there other molecules that might be able to get you access to this sort of a resonant energy transfer process?
Yeah, so I think in principle, I mean, you don't have to use this inversion doubling to do it, as long as the molecule has a dipole moment, and you can use rotational states to do this. Of course, you can use other parity doubling molecules. Other parity doubling molecules to do this as well, as long as there's a transition dipole moment.
Do you think you would target, like, if you were looking for like a specific energy gap and you would try and go find the molecule, or would you find the molecule first and then see what energy gaps were available?
Well, okay. I guess it depends on your application. Like I'm very familiar with this kind of cool atom cool molecule or rather, because you talked about cold in the project, but rather this ultra-cold atom, ultra-cold molecule type settings. But maybe do you mean like if you were a chemist and you were trying to look for a molecule and trying to detect certain things in a particular molecule?
I guess so, I'm more looking for like, is it motivated by the physics? Are there like physics knowledge gaps that then would tell you, okay, there's this energy gap that we need to specifically probe, let's go find a molecule that can get us.
Oh,
there.
I see. Yeah, like if you're trying to look for a particular transition.
Sure,
in
yeah.
something. I don't know, I don't know any particular applications of this to like a dipole transition.
Cause there's not anything
Yeah.
special about the 65 to 66 level, right?
Yes, there's not, it just happens to be activated resonant with
Yeah.
this ammonia.
Yeah.
So yeah, it's really the underlying process that you're kind of bolstering here. Yes.
This might be stupid, I might have missed something, but how do you treat the Rydberg atom core? Like what model do you use?
Yeah, so we do. So we kind of treat everything on the kind of intermediate range at the moment. So this kind of pertains to his question, Chris Green's question as well. So everything in the short range, we kind of bury under the hood. But we kind of imagine that, okay, because these are classical trajectories, there's some very, very low probability that you really collide with this helium-ion color. And so they're really just kind of these whizzing by transitions that barely perturb the plane wave as they go by.
So in other words, you're just using Whittaker functions with the correct quantum defect, I guess.
Yeah, I think in the formal language, that's yeah. But we're using it's plane waves that we're using to do this.
But I mean, I meant for the Rydberg wave function. That's not,
Oh, sorry. Yeah.
not a Whittaker function. Just
So
with the right quantum defect.
it was with the quantum defect.
Yeah, Rosario uses Whittaker functions.
Yeah, it's Rosario who does Yes.
Just how do you treat the singularity of big R in little r? Because when big R is equal to little r, in fact, you need an infinity of value of L to converge the potential.
You need a what, sir?
An infinity of value of L to converge the potential, no?
Field?
An infinite number, sorry, an infinite number of,
Oh.
of value of L.
Yeah,
to
so
converge
okay,
the potential.
I'm only expanding this Legendre functions, spherical harmonics to illustrate that there is such a transition. In the actual computation, we don't actually do this expansion. So we directly compute it on this charge dipole energy potential of here. Yeah, so we directly do the overlap integrals on this. Yeah, this is just to show that the transition is allowed.
Because on the curves that you show, one see really the singularity, by the way. You see it when big R is equal to, when you have this, yeah,
You mean this kink over here?
Yes.
Let's see.
no?
I think this is just from the Rydberg wave functions. So this doesn't occur.
Okay, so I mixed up.
Well, yeah, I mean, we never actually do the explicit expansion. Yes.
Just quickly back to, would it be crude to use like a Thomas Fermi model to treat the core?
You mean to get the Rydberg wave functions?
More crude than,
Probably. I'm not entirely sure. I haven't tried them myself. Sorry. Thanks.
Well, that would work better, I mean, for the very, very short range part. He's kind of not treating that because it's not the dominant part of the wave function. So I think it's more important to have the right energy of the state, which is what the Whittaker function does. It's just a Coulomb wave function at the right energy.
Thank you.
Any other questions for Reuben? If not, let's thank him again.